Today's separations class is all about how to solve the different genres of distillation column problems. We'll start in this video by considering the design type problems. In a design type problem, remember that you're being asked to determine the combination of the number of stages and the best feed stage and the reflux ratio that will achieve a target separation. When I say target separation, I mean that you're probably given some combination of what your target goal is of doing the separation. So that means you'd be given some combination of the four outlet variables, D for distillate flow rate, XD for distillate composition, B for bottoms flow rate, and XB for bottoms composition. You should start the problem by calculating whichever one of these four variables you're not given by performing an overall column balance, overall material balance on the column. In a true design problem of a distillation column, you won't be given either N, the number of stages, or R, the reflux ratio. And if this is the case, the problem is underspecified and you have 1 degree of freedom. So in class, what I'll do is likely set a value of R and you'll be asked to find the corresponding N. What you'll find is that the number of stages and the reflux ratio are inversely correlated. That means that as the reflux ratio increases, the number of stages will decrease. And I'll show you that in a moment. So a true design problem involves finding the values of N for many values of R, and then evaluating with a post-analysis which one of those combinations of the number of stages and the reflux ratio is best from an economic standpoint. We'll get to that soon. Let's look at the following example. A 100 mole per minute saturated liquid feed of initial composition 40% is to be separated such that the distillate purity is 90 mole percent and the bottoms purity is 5 mole percent. How many stages do you need if the reflux ratio is set to 3? The relative volatility of the components is 2, and the column has a total condenser and a partial reboiler. So the first thing you can do, because you have F, which is 100 moles per minute, you have Z, which is 0.4, and you have XD and XB, what you could do is you could calculate D and B with overall mole balances. I'm assuming here that all these purities are given in terms of component A because that's the only way that it would make sense. So let me just put that in there. Okay, after you have D and B, you could then calculate what L is, the liquid flow rate in the top of the column, by knowing what the reflux ratio is. With D and B solved, you can calculate L by knowing what the reflux ratio is, and you could also calculate B by doing a mole balance on the condenser in the rectifying section. Then you can assume constant molar overflow such that the liquid flow L and the vapor flow rate V are the same on each stage. Then, because of the assumptions of the split point and the total condenser, you can say that the composition of the reflux and the vapor coming off the top stage into the condenser is the same composition as the distillate product. Then the next step is to say that the liquid coming off of stage 1 is in equilibrium with the vapor from stage 1. So solving that equilibrium relationship graphically. Then you can solve the composition coming off of stage 2 and into stage 1 by solving the material balance, or alternatively by looking at the operating line on the graph and solving it graphically by using that equation for the operating line. Next step is to repeat steps 4 and 5, so do your stage stepping technique on your YX diagram, until the liquid composition coming off of the nth stage, whatever that happens to be, is less than the feed. So when the liquid composition is less than your feed for a saturated liquid feed, that is going to be the optimal feed location. I'll show you what that looks like on the graph in a moment. Then you want to change your step 5 to be the material balance calculations on the rectifying section operating line. Use the stripping section operating line instead. Finally, you want to repeat all these steps again until the liquid composition coming off of stage N is less than or equal to XB. And that will tell you what the number of stages has to be. So you count how many times you've done this repetition process, and keep in mind that the last stage is the partial reboiler since it's in equilibrium. Next, I'm going to show you a very cool resource that you can use on the internet to solve these distillation design problems very quickly. So on Google, search McCabe-Thiele calculator, and it's the first link that comes up. It's checalc.com, and it's a link from within there. So first link, when you search this on Google, And that strangely took me a while to load, but this is a very neat calculator that you can use. So you just input stuff from that problem. And I specifically chose, you have to have all the given information known in order to solve the problem this way, which is why I wrote the problem very specifically. Relative volatility for that example problem I just did was 2. The mole fraction of the feed was 0.4. The mole fraction of the distillate was 90%. The mole fraction of the bottoms was 5%, and my reflux ratio was 3. And my quality of the feed, my Q, is my, for this thermal state of the feed, it's a saturated liquid, which corresponds to a value of Q is equal to 1. All right, you may have noticed as I was typing those parameters in, this graph is going to change. So this is what your graph should look like. So it plots your rectifying section operating line automatically for you. It plots all 3 operating lines for you, actually. So the green one, this one here, let me zoom in a bit. This green one is your feed operating line. It has a slope that is straight vertical, corresponding to a Q value of 1. The rectifying section operating line should have a slope of 3/4, so that's R over R plus 1. And then the stripping section operating line, I notice I didn't put in what the boil-up ratio is, but it's connecting the point where the feed operating line meets the rectifying section operating line, and also intersecting the y equals x line at x is equal to b. So this is going to tell me what number of stages I need, and if you notice, it gives me a decimal amount. So you cannot have a fraction of a feed in real life, so you'd have to round this up. And the fact that you'd have to round it up signifies that when you actually build the column, you're going to get different purities than you expect, but you will exceed the purities that are specified. So this can kind of become a little bit of a predict type problem, where if I build the column with 12 stages plus a reboiler, which would be 13 equilibrium steps with a feed on stage 6, then I'm going to have slightly better than the compositions that I anticipate. But we'll get to the predict type problems later on in this class period. This resource is really useful for calculating what happens if you change certain things. So as I said, you can explore for yourself what happens when you change a parameter. So for example, let's say we change our reflux ratio. Instead of 3, let's say 4 now. And because of what I've told you, if reflux ratio goes up, we should be anticipating that the number of stages will go down. So if we change reflux ratio to 4, now the slope of my operating line will get steeper because it goes from 3/4 to 4/5 now, and I will need less stages. So now I only need exactly 11 stages, so that would be 10 plus a reboiler. Still feeding to stage 6. Notice at the 6th step, so 1, 2, 3, 4, 5. The 6th step is the one that steps over this point, and that is the optimal feed location. Still haven't talked about what happens if the feed location is not located optimally. In that case, it kind of becomes a predict type problem again, because you will have different purities than you expect if you put the feed in the worst place, or not in the best place. All right, so let's keep exploring here. If I decrease reflux ratio to 2 now my slope is getting less steep, and my number of stages is increasing. And let's see what happens if I try and decrease the reflux ratio even more, so like 1.5. Now I've got a problem where it says check input stages is greater than 100. So I've broken the McCabe-Thiele calculator by choosing a reflux ratio that's too low. And that's the first introduction to the concept that we're going to have a minimum reflux ratio and also a minimum number of stages. So that'll be the focus of the next video. But for now, notice that my minimum reflux ratio is probably somewhere around 1.9. Nope, it's even greater than that, 1.95. 1.95 is looking like close. So I'll show you the exact way that you can calculate the minimum reflux ratio without having to guess and check it. You can also calculate what is the minimum number of stages that I'd need. That's another interesting problem to have. So let's say I set the reflux ratio very high. Say I set it to 100. Even with the reflux ratio that is super high, I still need 7.6 rounded up to 8. So that would be 7 stages plus 1 reboiler for 8 stages total. 8 equilibrium steps in order to make this separation happen. So like I said, the next video coming up will tell you how to analytically solve for the number of stages, minimum, and the minimum reflux ratio for design type problems.